a video on that topic and upload it on my channel. If you can make a video on that topic, you can also make a video and send the video to me. I will upload your video on my channel. In lieu of this, I will share my privacy code with you. You can send me a personal message through Telegram channel, through mail, through WhatsApp message. I will be thankful to you. Let's start. In this video, I will discuss about number of codes of SOI MOSFET. Almost complete study of SOI MOSFET. I have already made a video about basic of SOI MOSFET in my previous lecture. In this video, I will give you a complete detail of SOI MOSFET. Most of the people send me the inquiry about partially depleted, fully depleted SOI MOSFET, kink effect in partially depleted MOSFET, comparison between partially depleted and fully depleted SOI MOSFET on the basis of leakage current analysis. So that in this video I will discuss four Silvaco codes of silicon on insulator MOSFET with you. First code is based upon partially depleted threshold voltage and subthreshold slope analysis. Second code is kink effect in partially depleted SOI MOSFET. Third code is fully depleted threshold voltage and subthreshold slope analysis. And the last code is partially depleted versus fully depleted leakage current analysis. First, what is SOI? SOI is silicon on insulator technology, refer to the use of layered silicon insulator silicon substrate in place of conventional silicon substrate in semiconductor manufacturing to reduce parasitic device capacitance, thereby improving the device performance. The transistor structure then resides on the thin silicon film. It is compatible with the conventional silicon technology. Based upon the thickness of the silicon film and doping concentration, it is further categorized as partially depleted or fully depleted SOI MOSFETs. SOI MOSFETs offer several advantages as compared to bulk MOSFET, such as excellent lateral and vertical isolation, improved latch-up free operation, reduced leakage current, reduced short channel effects, and improved switching speed due to reduction in the drain body capacitance. Now, first is partially depleted SOI MOSFET. SOI MOSFET are divided into two categories. I have already told you, partially depleted and fully depleted SOI device. In case of partially depleted SOI MOSFET, the silicon body is thick enough so that the gate depletion region does not extend to the entire silicon body thickness to the buried oxide. You can see in the figure, the upper portion is depleted and the lower portion is not depleted due to thickness of silicon material or substrate. Partially depleted SOI devices have silicon thickness greater than 0.15 micrometer, or we can say that greater than 150 nanometer. The depletion region extends into the body of the device under the gate at the source body and drain body junctions and does not deplete all of the charges in the body, resulting in the name partially depleted SOI. The increase in the body charge gives rise to the body potential that result in the kink in the output characteristics, that is well known is the kink effect. Partially depleted SOI MOSFET analysis on the basis of threshold voltage and subthreshold slope. This proposed structure simulates the ID versus VGS characteristics of a thick film SOI MOSFET and from these results extract the threshold voltage and subthreshold slope. These are two key parameters, subthreshold slope and threshold voltage, involved in the design of SOI MOSFET. It demonstrates basic SOI structure definition using Atlas syntax, setting transport model including impact ionization, generating an ID VGS curve with VDS is equal to 0.1 volt, extracting threshold voltage and subthreshold slope from the results, plotting output curves and structure file. The proposed SOI devices is a partially depleted device composed of zero point 0.2 micron layer of silicon, or we can say that 200 nanometer length of silicon, and 0.4 micron or 400 nanometer silicon dioxide substrate. The proposed device has a 17 nanometer thick gate oxide and a gate length of 1 micron or 100 nanometer. For simplicity, there is a no silicon below the back oxide. Other example in this section do include a silicon substrate. Let's go to the code. This is the code of partially depleted SOI MOSFET. The device meshing, reason, and material specification and electrode definition are performed using mesh, reason, and electrode statement at the start of the input file. You can see that the code started with the command go atlas with dimension is mentioned here, 200 nanometer thickness of silicon and 400 nanometer thickness of the oxide substrate. You can note down X meshing and the Y meshing. X meshing start from the 0 and end at the 300 nanometer, and the Y meshing is starting from the negative value 17 nanometer to the 600 nanometer with different value of spacing. Next is the reason and the material statement. Reason number 1 having the oxide material, reason number 2 having the silicon material, and the reason number 3 is again having the oxide material with their positional parameter. Next is the electrode statement. The first electrode name is gate, second electrode name is source, third one is the drain, and the last one is the substrate. Every electrode is mentioned with their positional parameter. Next, I have defined the doping statement. The doping is added as simple analytical functions. The chemical doping in the example is considered as uniform. The source and drain profile are considered as Gaussian doping. No spacer is considered in this case. After the structure description, the interface statement is used to define the fixed oxide charges on both sides of the silicon and SiO2 interface. You can see that the charge density is 3 raised to power 10 with the positional parameter and 1 raised to power 11 with positional parameter. Next, the contact statement is used to specify the work function on the polysilicon gate. The gate work function is mentioned with the material polysilicon. Next, I have defined the model statement. The model statement is used to specify a reasonable set of physical model for SOI simulation. In this case, the concentration, dependent mobility, SRH recombination, Auger recombination, band gap narrowing, and parallel electric field dependent mobility are specified in the code. After the model statement, apply the voltage to the various terminals. First, solve initial. After this initial condition, a negative gate voltage is applied, followed by a solution at drain bias of 0.5 and 0.1 volt are applied. You can see that in the code I have defined the source statement. First I had given the gate voltage minus 0.2 volt. After that the drain voltage 0.05 and 0.1 volt. Before that I have mentioned the method statement Newton and trap. Next, the log statement is used to specify a file for collection of ID versus VGS characteristics of the SOI device. These characteristics are captured with the following solve statement, where the gate bias is ramped in 0.1 volt increments from minus 0.2 volts up to 1.5 volt. After the voltage have been solved, external statements are used to find the threshold voltage and subthreshold slope of the SOI MOSFET. You can see that after the Tony plot, I had mentioned the extract statement and I have applied shortcut code to find out the subthreshold slope and threshold voltage of the partially depleted SOI MOSFET. Last one is quit statement. When you run the program, you will get the two files. One is structure file and one is log file. In the variable history, you can check the subthreshold slope is approximate 107 dB and the threshold voltage is about 1 volt. You can see here. This is the structure file, 200 nanometer silicon thickness and 0.2 to 0.6 400 nanometer SiO2 thickness, and above this and the top of this structure, this one 17 nanometer SiO2 thickness. This is the log file of the partially depleted SOI MOSFET. If you want to check in the log form, click on this log. Okay, the off state current is approximate 10 raised to power minus 14 and the on state current is approximate 10 raised to power minus 5 in the case of partially depleted SOI MOSFET. Next, we will talk about the kink effect or second code. The kink effect is observed in the partially depleted SOI MOSFET devices. In these devices, the electric field near the drain region will be high due to relatively higher drain voltages. Second point, consequently the channel electron in the high electric field acquire high energy and create electron hole pair by impact ionization mechanism. The generated electrons are collected by the drain and the holes accumulate in the floating body. The accumulation of holes in the floating body leads to increase in the body potential, and the associated drop in the threshold voltage lead to a sharp increase in the drain current. The increase in the drain current further leads to an increase in the number of holes generated. This cumulative process will continue until the body source junction is forward biased, allowing the holes to exit the device. Consequently, the device will not be suitable for linear application due to the non-linearity created by the kink effect. In the code of kink effect in partially depleted SOI MOSFET, this example simulates the ID versus VDS characteristics of a partially depleted SOI MOSFET for 3 gate voltages. The effect of impact ionization at the drain junction causes the silicon film to be raised in the potential and causes a shift in the threshold voltage. This is seen as a kink in the ID versus VGS curve. The file shows basic SOI structure definition using Atlas syntax, setting transport model including impact ionization, generating an ID versus VDS curve with VGS 1 volt, 2 volt and 3 volt, plotting the output curves and structure. Let's go to the code. Let's start with the second code, kink effect in partially depleted SOI MOSFET. Let's start with the second code, kink effect in partially depleted SOI MOSFET. The first command is go atlas. The device has the same dimension as the previous device. 0.2 micrometer of silicon thickness, 200 nanometer silicon thickness and 400 nanometer oxide substrate. Next is the X meshing and the Y meshing. Same dimensions, same meshing. X meshing is start from the 0 to 3 with different spacing, and the Y meshing is start from the negative value minus 0.017 17 nanometer to 700 nanometer. In the last code, I have taken the Y meshing up to 600 nanometer. In this code, the Y meshing is taken up to the 700 nanometer. After the meshing, I had mentioned the region statement with the material. Region number 1 having oxide material with their positional parameter. Region number 2 having silicon material, and the region number 3 is again having oxide material with their positional parameter. Next is the electrode statement. I have defined all the terminal gate, source, drain and substrate terminal with their positional parameter. Next, I have defined the doping statement. Source and the drain having Gaussian doping and the channel having uniform doping. You can note down from the code. Next, I have defined the interface statement. I have already mentioned that interface statement show the fixed charge density at the silicon dioxide interface. Next, I have defined the context statement, model statement, and the method statement. Next, the impact statement is used to specify that the Silvaco impact ionization model is to be used. After the initial solution, I had mentioned the method statement with neutron trap method. After that, I had mentioned the drain voltage 0.05 volt and 1 volt. And the most important thing to be noted in this code. Next, I have defined the ramp gate voltage from 1 volt to 3 volt, in which I found the three structure files for different three gate voltages VG1, VG2 and VG3. I had given the name SOI1, SOI2 and SOI3 structure file. After obtaining the three structure file, I had applied the drain voltage from 0.1 to the higher voltage 3.3 volt. You can note down. Please note down the code very carefully. You will get the same result as I got. Next, I had applied the drain voltage to all the three structure code, all the three structure file obtained from the VG1, VG2 and VG3 code. And the last one is the Tony plot overlay statement. This statement is used to obtain three graphs in one file. From the log file, you can observe that there is a change in the threshold voltage when you change the drain voltage from 0.1 to the 3.3 volt at fixed value of gate voltage. When you run this code, you will get the two files. One is the structure file and one is the log file. First, I will go for the log file. This is the log file I got from the code of kink effect in partially depleted SOI MOSFET. SOI1 red line showing the gate voltage VG 1 volt. Second one SOI2 is showing VG 2 volt and the SOI3 is showing VG 3 volt with the change in the drain voltage. You can note down that the threshold voltage is changing. If you want to find out different parameter, you can also find from the structure file. I will go to the structure file. This is the structure file overlay in one file, SOI1, SOI2 and SOI3. This is the electric field. You can note down that if you are increasing the gate voltage, the electric field is increasing at the channel region. From the second diagram, you can note down that if you are increasing the voltage, the potential in the channel region is increasing in the upside. Next is the fully depleted SOI MOSFET. In case of fully depleted SOI MOSFET, the silicon film beneath the gate is depleted throughout the box. One of the most attractive features of the fully depleted SOI MOSFET is its reduced body effect coefficient. The reduction in the body effect coefficient helps to increase the drive current, transconductance and improve subthreshold flow to near the ideal value approximate 60 millivolt per decade. You can note down that the thickness of the SOI is less in case of fully depleted SOI MOSFET. Fabrication of fully depleted SOI devices involves development of ultra-thin body and therefore needs more sophisticated technology. The threshold voltage in partially depleted SOI devices is relatively less sensitive to the uniformity in the silicon film thickness. In the fully depleted SOI device, The threshold voltage depends on the silicon film thickness. It is difficult to control the thickness of ultra-thin film body in fully depleted SOI MOSFET, and as a result, the film thickness becomes non-uniform across the wafer. For this reason, there has been a growing interest in the partially depleted SOI MOSFET. Let's go to the code of fully depleted SOI MOSFET. Before go to the code, I will discuss some point with you. In case of fully depleted SOI MOSFET, we have done the analysis on the basis of threshold voltage and sub-threshold slope. This proposed structure simulates the ID versus VGS characteristics of a thin film fully depleted SOI MOSFET demonstrate. Basic SOI structure definition using Atlas syntax, setting transport model including impactanization, generating an ID versus VDS curve with VDS 0.1 volt, extracting threshold voltage and sub-threshold slope from the result, plotting output curve and structure. Thin film fully depleted SOI MOSFETs have been shown to achieve low sub-threshold slope and near ideal inverse sub-threshold slopes. This makes them ideal for the low power operation. This example demonstrates that Atlas is capable of reproducing the difference between a partially depleted transistor in the previous example and the fully depleted transistor in this example. The mesh has been modified to support the thinner SOI film thickness of 100 nanometer, and the definition of the SOI layer on the region statement has similarly been adopted. Similar change has been made in the region statement also. Also, the channel doping has been reduced on the doping statement to ensure the film is fully depleted. Let's go to the code. My dear friend, this is the third code of fully depleted SOI MOSFET. Again, start with the same command go atlas. This device having different dimensions as compared to partially depleted SOI MOSFET. In this case, the silicon film thickness is about 100 nanometer and the oxide thickness is again 400 nanometer. The meshing in the X direction start from the 0 and end at the 300 nanometer. In case of Y direction, the meshing is again start from the minus 17 nanometer up to 500 nanometer. After that, I had mentioned region statement, region number 1 oxide, region number 2 silicon, and the region number 3 is again oxide with different position parameter. Again, I have defined the electrode statement for all the 4 terminal with their position parameter. After this, I have defined the doping statement, channel having the uniform doping and the source and the drain having Gaussian doping. After that, I have defined the interface statement. I have already tell you about the interface statement. Next is the contact statement. After that, I have defined the model. Next, I have applied the different voltages at different terminal, gate, drain and source terminal. Next, I have applied the extract statement to find out the sub-threshold slope and the threshold voltage, and the value of this you are checked from the variable history. The sub-threshold slope initially in case of a partially depleted MOSFET it is about 107 millivolt per decade, but in case of fully depleted MOSFET the sub-threshold slope is reduced to 72 millivolt per decade, and the threshold voltage is about 1 volt in case of partially depleted SOI MOSFET. Now it's reduced to 0.49 volt in case of fully depleted SOI MOSFET. The main point in this code is to note that the mesh has been modified to support the thinner SOI film thickness of 100 nanometer and defining the SOI layers on the region statement with different position parameter. Also, the channel doping has been reduced on the doping statement to ensure the film is fully depleted in this structure. When you run this program, you will get the two files. One is the structure file and one is the flow file. This is the structure file: 100 nanometer silicon thickness, 400 nanometer oxide thickness. Next is the log file. When you check that the subthreshold slope is improved and the threshold voltage is reduced to approximate 0.5 volt. This is the two advantages of the fully depleted MOSFET. Now I will move to the last code, partially depleted versus fully depleted leakage current analysis. Or we can say that the comparison between the partially depleted and the fully depleted on the basis of leakage current. This code simulates leakage current at high drain bias and show how this value can be extracted as a design parameter. The analysis is repeated for both fully depleted and the partially depleted SOI MOSFET. It demonstrates basic SOI structure definition using Atlas syntax, deck-built syntax for defining general structure dimensions, setting transport model including impact ionization, generating an ID versus VDS curve with VGS 0 volt, extracting the leakage current design parameter, plotting the output curves and the structure. The leakage current in SOI MOSFETs has in the past been seen as a barrier to its development. The source of the current has in some cases been, been due to the existence of the interface charges at the bottom oxide silicon interface. This example simulates the leakage current analysis for both partially and fully depleted SOI MOSFETs. In this example, rather than use two Atlas input files for thick and thin SOI films, a more general purpose input files has been created. By using deck-built set commands, it is possible to create variables inside the input file. These variables may then be used to define the location of mesh line or region boundaries. In this example, we are not creating two different codes for partially depleted and the fully depleted SOI MOSFET. We are using the single code. By using the deck-built set command, we can run the same code for the partially depleted SOI MOSFET and the fully depleted SOI MOSFET. So let's move to the code to understand how it is possible. This is the last and the final code for the partially depleted and the fully depleted leakage current analysis. First, I will discuss the fully depleted leakage current analysis. Again, the code start with the go-atlas command. These are the three deck-build set commands that will decide whether the code is worked on the fully depleted SOI MOSFET mode or partially depleted SOI MOSFET mode. Initial, I had given the value according to the fully depleted SOI MOSFET. Silicon middle is about the 50 nanometer, silicon board is about the 100 nanometer, and the oxide board is again at the bottom is 500 nanometer. Next, I have defined the X meshing starting from the 0 to 300 nanometer with different spacing. Again, I had mentioned the Y meshing for negative value of 17 nanometer to the maximum value of oxide board. I had mentioned that 500 nanometer 0.5. You can check above at the initial starting condition. The y.mesh definition has been modified to use the created variable to define the location of y mesh lines, and in a similar manner the region statement has also been changed to use these variable to define the region boundaries. Next, you can check the region statement. One is for the oxide, second is for the silicon material, and third is again used for the oxide. Next, I had defined the lactose statement. The lactose statement is for the gate, drain, source, and substrate terminal with their positional parameter. Next, I had defined the doping statement. The channel having the uniform doping with their positional parameter, and the source and drain has Gaussian doping with positional parameter. Next, I have defined the interface statement. Interface statement is mentioned with the positional parameter with variable parameters. Interface charges on both top and bottom interfaces are defined on the interface statement. In SOI MOSFET, these two interfaces can have very different value of interface charges as shown in the example. Once again, the predefined variables have been used to define the region where the charge exists. Next, I have defined the contact statement. After that, I had defined the model statement. Next is the impact statement. Submicron devices should be simulated using the energy balance model due to velocity overshoot and the non-local impact ionization effects which could be substantially influence device characteristics. The model HCTE statement is used to set the solution for electron and hole energy balance. Next, the impact statement is used to specify that the Silvaco impact ionization model is to be used. Impact ionization is an important phenomena in SOI devices even at relatively low voltages. The impact model is required here for the SOI ID versus VDS analysis. Next, I had applied the different voltages at the drain and the gate terminal to simulate the same code for the thick film partially depleted transistor case. The set statement need to be changed. The value of the set statement set silicon middle is changed into zero point 0.2 200 nanometer and the value of silicon board is 0.4 400 nanometer and the oxide board is 1 is almost double 100 nanometer. Before to run this program you can note down that the value of the ID leakage in case of fully depleted SOI MOSFET is about 2.87 into 10 raised to power minus 40. You can check here also. When you run this code, this program is running for partially depleted SOI MOSFET. The value of the predefined parameter are changed into silicon middle is 200 nanometer, silicon board is 400 nanometer and the oxide board is 100 nanometer. After the end of this program, you will get the value of the leakage current for the partially depleted SOI MOSFET. You can note down that the value of the leakage current is changed into 3.45 into 10 raised to power minus 40. You can note down that in case of partially depleted SOI MOSFET, the leakage current is increased to the 3.4 into 10 raised to power minus 14 ampere per micrometer. This is the structure file for the partially depleted leakage current analysis. Drain current with respect to the drain voltage from 0 to 3.3 volt. This is the log file to the fully depleted leakage current analysis. From 0 to 3.3 drain voltage. The curve is again plotted between drain current and drain voltage. If you want to compare these two log files, you have to overlay one log file to the other log file. Two log files in a one plot. Red one is for the SOI fully depleted leakage current analysis and another one is SOI partially depleted leakage current analysis. You can note down that the leakage current is high in case of partially depleted SOI MOSFET as compared to fully depleted SOI MOSFET. Please note down the code very carefully. You will get the same result as I obtained from these 4 codes of SOI MOSFET. Thank you, my dear friend. This is end for today.